Previously, I've made 3 videos on spring elements shape function, the string energy stored within the elements, and also development of the stiffness matrix based on minimum potential energy. If you don't understand the theory in detail, if you don't completely understand it, that's okay, but you must know how to use them. Okay. In this video, I'm going to show you one example. Please take a look at the diagram here. We have a rod attached to the wall, and there's a force acting on it. Please pay attention. Previously, what we learned is a force acting on the node only. But right now, we have a force acting along the rod. And the force acting on it is a function, as a function of x. Okay. The geometry of the rod is a uniform area. Cross-section area is 1 inch square, and the materials is a uniform materials all across it. It is a 1000 psi. So the stiffness is a EA over L, and the matrix stiffness matrix is a 100, 100, negative 100, and negative 100 along the other side. Okay. Now take a look at the force vector. Okay. So let's see, we are using the shape function here now. Okay, so we took the integrations of the force acting on the shape function. Okay, the spring element's shape function is 1 minus x over L. In this case, L for one element is 10. Okay, so we take the integration of that. We have this formula and plug in the BC, the boundary condition, which is from 10 to 0. Okay, so the force vector for the first element is 50-50. Now let's take a look at the second force element, so which is acting 20 from 10. Okay, and plug in the numbers. The second force vector is negative 50 and 150. Now we have the bit and pieces for the local elements. Let's put them together. Okay, let's work on the stiffness matrix first. That portion contains the stiffness matrix for the first element, and this is the second element. Now U1, U2, and U3, we know U1 is not moving at all, so we put it at 0. Okay, and let's assemble the total force vector. Okay, this is the portion for the first elements, and that's the force acting on the second element. We know there's a reaction force that holding to the rod against the wall, so when I'm pulling the force acting on it, that reaction force is keeping the rod in place, so we need to put a reaction force there. Okay, now we have 3 equations and 3 unknowns. Yes, we can solve that after a few row reduction method, and we find out U2 is 1.5 inch and U3 is 3 inches, and we plug in those numbers, and we have a reaction force at negative 200 pounds pulling on the rod, so the rod stay in place. Thank you for your attention.